Okay, so remember what we were doing. So we arrived at a determinantal formula for the number of CSPPs inside an A by box. It's this complicated looking determinant for which I showed you how the entries look like on Sage. And I said that using similar methods, Andrews was able to evaluate the number of descending plane partitions, which are strict shifted plane partitions with this extra condition, two extra conditions. Number of parts in each row is less than the largest part in that row and is greater than or equal to the largest part in the next row, the following. And this was an example. And after the class, I sort of added that also to Sage, and I did showed some example. Andrews again, although he formulated both of these as determinants, he was not able to evaluate them. This was, but he was able to evaluate this particular determinant when q equals 1, and he obtained the ASM. So remember at the beginning of the course I mentioned 3 families of objects counted by ASMs, and DPPs was one of them. So he managed to show it. So I will. So now let me continue the story. I will not go into too much detail, except to say that Mills, Robbins, Ramsey proved Town's conjecture by evaluating a more general determinant the general determinant, which is the following. So this is the determinant of again delta ij plus t times q to the I plus 1 minus d, the q binomial coefficient I plus j minus d, j minus 1 base q. And this is an A by A determinant. So here d and t is an integer and t is a parameter. They called it lambda there, but since I'm going to show you on Sage, and lambda is not allowed. I thought it was t. Okay, so this is this. So I called this the Mrr matrix, that's Robinson matrix, and so in general, so let me just take q and t arbitrary for now. So if I take even for 3, this is not nice. So it's going to be something, it doesn't factor. But 2 special cases, so they used tricks. So here they used tricks from linear algebra. And the theory of hypergeometric series. To evaluate. Well, they didn't really evaluate this, but to prove the condition. So I refer you to chapter 5 of Pursuit. So for lack of time, I'm not going into hypergeometric series theory. But two special cases I should mention. So setting t equals q and replacing q by q cubed, and d equals 2 gives CSPP matrix. So let me show you that. So if I put t also equal to q and I replace q by q cubed, then I get this factorization, and if you compare with the CSPP matrix, this is what it is. You can see that it's the same. And if I take, so the second case is, if I take t equal to 1 and d equal to 0, you get TPPs. So both of these are special cases. So let me show you that. So I take t equal to 1 and d equals 0, and q is q. Then I get this using partitions. That. So here let's evaluate I should define this. And you see it's the same. Okay, so those two are special cases of this matrix. So I will not say much more about this. This is a fairly long-winded proof, and one has to introduce. I mean, there's a lot of background on hypergeometric series which one has to go through to be able to prove this, but I leave it. I leave it for you to go through if you're interested. Let me come here. Okay, so now I want to start a new story. So, are there any questions about this? So, yeah, so the main thing I did in this CSPPs is to arrive at the determinant formulation, which was itself not completely trivial. Okay, so now I want to move to the the last class of plane partitions. These are TSSCPPs in 2n by 2n. And here is an example. So, as usual, stolen from Bristol's book. So this is an example. So what are TSSCPPs? They are totally symmetric self-complementary plane partitions, and they have the maximum possible symmetry. So they are symmetric under vertical reflection, about cyclic rotation, and you can see that over here. They are also so that implies that they are totally symmetric. So they have all the symmetries of D6, the dihedral group of the hexagon. I mean the dihedral symmetries of the hexagon. Further, they have complementation symmetry. That is, they are self-complementary. That's the SC over here. And so if you remember from this cyclic symmetry, you have to have the A, B, and C all equal. And by because of the complementation symmetry, you have to have that this A has to be even. It has to be an even integer. So this is such an example, and this is just to illustrate that even though they have a lot of symmetry, there is quite a bit of structure here. I mean, it's not; these are not completely trivial objects. Okay, so I'll come to the decomposition. So let's talk about how one can begin to enumerate this. So first of all, you can see that this part over here is the same as this part, is the same as this part, and by complementation, this part is, depending on your choice, is the same as this part. And this is the same as this is the same as that. And so it suffices to look in this general region. So this is 2n equals 5. So this is, if I look at this 5 by 5 by 5 box, all the information is there. So by the symmetries, it suffices to look in any n by n by n corner. So either this n by n corner, this one, all of them give you the same information. Right? So because of self-complementarity, so before that we will decompose the TSSCPP into shells, just as we did for cyclically symmetric. Okay, but by self-complementarity, it suffices to focus okay, so maybe I'll say this afterwards. So we start with the outer shell. First shell, that is the outer shell. So let's look here. So the outer shell consists of, if you remember, going back to our CSPP case, it consists of cells whose first coordinate is 1. One of whose coordinates is 1. So these are the cells over here and over here. These cells is like that, right? But we have self-complementarity, and so instead of looking at all these cells, I mean, we can look at just the cells on this top row. So that will contain all this other information. So just to give you an example, so these cells over here, well, okay, so let me say, just as for the partition case, the n by n by n box inside in this inner corner, well, maybe any corner, any n by n corner except the inner one. Right, the innermost n by n corner has to be occupied. This is the same argument as for self-complementary partitions inside an n by n box, inside a 2n by 2n self-conjugate partitions inside a 2n by 2n box, the problem that we did in the midsem, So we will look at any of these outer boxes, and so if I outer n by n boxes, so I prefer to choose this one. So as I said, all the information is there, so it's enough to look at the boxes one whose last coordinate is n, is 2n. Okay, so those are these boxes. I mean, just to give you an idea, so look at this box. I mean, you have this staircase shape, and those are precisely the ones which are missing from here, and ditto for here, and these are of course the same. So it suffices to focus on boxes one of whose coordinates is 2n, and by total symmetry we look at boxes of the form ij comma 2n for 1 less than or equal to ij less than or equal to. Okay, so we're going to look only in this area, and here these are these boxes. So the first shell is this. So the first shell, for example, first shell in our running example is this partition, or can be written as the partition, this one, which is 5, 5, 4, 3, 2. So what do you notice about this partition, or any of the partitions in this n by n box? Anybody?
They're symmetric.
That's yes, they are self-conjugate, exactly. So if you reflect about the center, I mean about the vertical axis, so so by a general result, or maybe I should leave this as an exercise. So partitions, self-conjugate partitions of n are in bijection, natural bijection with partitions of n into odd distinct parts. Not an exercise. I'll just a remark. So why is this? I mean, this is kind of obvious from the Young diagram. So the idea is to read the partition using diagonal hooks, diagonal hook lengths. Right. So if you have a self-conjugate partition, that means every hook length corresponding to a diagonal cell is going to be an odd integer, because the row length is going to be equal to the column length, and you have an extra cell over there. So we are going to reinterpret this partition as the partition 973. So 9 is this length, 7 is this length, and 3. And the distinctness comes because this is a partition, so you don't want any overhangs. So these will be odd and these will be distinct. Okay. I don't know if I gave this as a homework problem earlier, but it's easy to see. Okay. So okay. So example, the partition is 973. Okay. So read the partition as 973. Okay. I'll move this to later. Good. This first. Okay. So okay, this also should have gone down, but okay. Okay, so we'll read this partition as 973. Now, what do you do with the second shell? So the second shell. Oh, sorry. The second shell is formed by boxes whose boxes of the form ij 2 and minus 1. So you have removed the top shell, but you have also removed the behind. So so instead of ij starting from 1, ij will start from 2. So let's go back to this example. So this is the top shell. So imagine you have chopped it off. The next shell is, if you can see, is the partition 55533, right? But we have removed the first shell, so that in effect means that you have also removed the first row and the first column. So you subtract, so it has one less part, and each part length is one less. Right? So so in the example, we get the partition 4422. So yeah, okay, so I'm not explaining that. And if you read that, this is 4422, you get 7 and 5. Similarly, the kth shell for 1 less than equal to k less than equal to n is given by boxes of the form I, j, 2n. So this was the second shell. So plus 1 minus k, where k is less than equal to I, j is less than equal to. Right? So let's see the third shell. So the third shell, if you can imagine it, is 655432, and we remove the first two entries, and we delete 2 from the other. So you get, so if you look here, you will get 3, 2, 1, I believe. Yeah, it's 3, 2, 1, and that's in this language is the partition 5, 1. And then the fourth one, example, third shell is a 3, 2, 1, which we interpret as 5, 1. The fourth shell, you can see I'm trying to cover this page because I don't want to start with that example in the next page. The fourth shell is this rather large partition, but we have to remove the first 3 rows, so I can, and the first 3 columns, so I can forget all this. So then I just have the singleton partition 3. That's that. Well, the partition is 2, 1, and that has to be read as 3. And the fifth shell is, okay, let's go here. So this is the last guy, which is this rather huge partition, but we have to remove 4 rows and 4 columns, and at the end you are left with this, just the singleton. So this is the partition 1, which also is interpreted as well. So an exercise for you to think. It's kind of easy. So if you look at what happens for k equals n, you will get n, n, 2n plus 1 minus n, which is just n plus 1. So in fact, the last shell will always be a 1. So let's say note. The note, the nth shell is always. Okay, so let's look at this example. So these are all TSSCPPs inside a 6 by 6 place. Okay, there are 7 of them. There's the number of ASMs. You can see some are pretty simple, have virtually no structure, but others are quite rich. Okay, so let's for each example, let us write the distinct dot partitions. So let me move this up, and let me write the distinct dot partitions. So let's write the distinct odd partitions in the same order. Okay, so let's write this for the first one over here. So I will write this separating the partitions by yeah, why don't you tell me? So what is the first partition of this guy, the outer shell, in the distinct odd language? Yeah.
5 1.
That's right. 5 1 is the first one. Maybe I'll write it a little inner, right, so I have space for this. So 5 1. Okay. What about the next one?
3 1.
3
3
1.
1.
Very nice. So does everybody see it? So you remove the first row and first column, and you have the 2 by 2 box, which is self-conjugate, and you write it in this language. You get 3 1, and the last one, as I said, is always 1. What about this guy?
5 1 and then 3.
And then, right, exactly. So then there's just this singleton, the partition 2 1 over here, which is 3, and then this one. Okay. Now, okay, things are getting more complicated. What about this guy?
5 3.
5
5 3. Very good. And then next.
3.
Yeah, and then this you have to look at this box, which is 3, and then 1. And this guy?
5
Just 5, yes.
3 1. I mean
3.
3 and then 1.
Yes, exactly. Yes. So this is the bare bones. This is the simplest thing, and you can see it has this kind of staircase shape, or whatever. Maybe staircase is not the right word, like a step well. Okay. This one is again 5 outside, and this is 3 1, and then 1. I'll do the rest. And this guy is now 5 3. This is this part, same as this. The next one is 3 1 as opposed to this, and the last one is always 1. And this one is the biggest one, so it's 5 3 1, and then you have a 2 by 2 box, which is 3 1, and then you have 1. So okay. So you can see all are distinct. And they have certain structures. So okay, so I'll come to that. Maybe this example is too small to illustrate what's going on, but let me explain the general structure. So as before, we will try to arrange these partitions in some kind of plane partition, and now let's see what's the comparison. I mean, okay. So the first shell is over here. So okay, let's look at this example. So this corresponds to this shell. So let's go back to the first example. So let us look at the first partition in this distinct odd language of the second shell and see what it needs to compare to with the first shell. So the first shell, the first partition of the first shell is the outermost, and it does not really interact with with the first partition of the second shell. Rather, what interacts is the second entry of the partition of the first shell with the first entry of the partition of the second shell. I'm sorry if that sounds confusing, but I'll write down the general statement. So it is clear that the first, or rather the second entry of the partition, or second part of the partition in the first shell is less than or equal to the first part of the partition in the second shell. Otherwise, as I said, there will be overhangs. So you want this guy to be sitting strictly above this the guy below it. So this part, this 7 over here, is less than or equal to the first part, which is 7 over there. So this 7 is less than or equal to this 7, this is not equal to 7. Okay. So similarly, the ith part of the jth partition is less than or equal to the I minus 1th part of the j plus 1th partition. So this implies we can arrange these partitions in an SSPP, that is strict shifted plane partition, like array. So in our example, this would be 9, 7, 3, 7, 5, 5, 1, 3, and 1. Okay, so where you can see that the entries are weakly increasing down rows, strictly decreasing down columns, and contain odd integers. And of course, you know, it's a subset of this triangular. Okay, so let's write down a general definition. An array of positive odd integers aij 1 less than equal to I less than equal to j less than equal to n is called a TSSCPP array of order n if first of all, aii is 2n plus 1 minus 2i. Second is strict decrease along rows and weak decrease down columns. Weak increase. So again, to write down the example for n equals 3, so all TSS arrays of order 3, I'll write it in the same arrangement as these. So let me write it down. So you can look at it later. I have it from my notes. So 5 1 3 1 1 5 1 3 1 5 3 3 1 5 3 1 5 3 1 1 5 3 3 1 1 and 5 3 1 3 1 1. And let us see that they are all of them. So the diagonal is always this is fixed. It's always the same. And this is also a property of the TSSCPP. So this is maybe something I'll leave as an exercise. Okay, what else? So let us see that we have all of them. So the diagonal is first, and now let us see what possibilities are there above the diagonal. Well, you can have 1, 2 or 3 entries above the diagonal. If you have 1, it can be either here or here. Well, if there is none, then this is the only one. That's here. If there is 1, it can be here or here. So if it is here, there are 2 possibilities. It's a 3 or it's a 1, or it's a 1. That's here. Or if it is here, there's only one possibility. It has to be a 1. That's over here. Now, if there are 2 entries, they have to be these 2. You cannot have either these 2 or these 2. So they have to be these 2. This always has to be a 1. This can be a 1 or a 3. So you get these 2. And if it's all of them, you have this. So you can see we have all of them. And this is the general proposition. So this so this is, I don't know who wrote it down. Maybe Ms. Robbins Ramsey wrote it down, or maybe Andrews wrote it down. I don't remember. So there. There is. Sorry about that. There is a bijection. Between TSSCPPs inside inside a 2n by 2n box by 2n by 2n box and TSSCPP arrays of order. So now let us try the strategy of going to non-intersecting lattice paths. So we want to translate these arrays as non-intersecting lattice path families. Okay, and okay, so now things get a little more complicated. So let me show you the problem. So okay. So the starting points are the Si, which is 2 minus 2i, comma I minus 1. I'll draw figures soon. 0 less than equal to I less than equal to n minus 1. Ending points EI. The problem now is that they do not, you cannot, there's no way to formulate this as non-intersecting lattice paths where the EIs are fixed. Instead, what we can say is that the EIs lie on the line y equals 1 minus x, and we use upright steps as usual. So let me show you with our running example. So running example. Okay, so let me go to graph. So I need much better. Okay, so these are not the xy axis. Okay, so I'm just drawing them to give myself some frame of reference. Okay, so let me see if I have enough lines. 1, 2, 3, 4. Ouch. So let me mark this point. So this is 2 comma minus 1, and this is 0 comma 0. This is minus 2 comma 1. Okay, I'll take it. This is minus 4 comma 2. This is minus 6 comma 3. And so this is S1, S0, sorry. This is S1, this is S2, this is S3, this is S4. And let me draw the line y equal to x, y equal to 1 minus x. So it will also pass through this line, so I'll use another color. Okay, so this is going to be a bit difficult for me to draw. I'll try. So let's see if I can do it. Okay, not bad. Okay, so it passes through these lines, and so this line is kind of useless. Okay, so okay, and now I want to write some labels. Okay, so we'll use this color. So what we will do is we will let me maybe explain. We will mark horizontal edges below the line y equal to 1 minus x, which is this line, with consecutive odd integers. So what did I say? So this will be 1, 3, 5, 7, 1, 3, 5, 1, 3, 5, 1, 3. That's enough. 1, 3, 1. Okay, so okay, so let me write that again. So this is y equal to 1 minus x. And now let me draw the paths corresponding to our example. So let me remind you what the example is. So our example is 9, 7, 3, 7, 5, 5, 1, 3. Okay. Okay. So this. So what we will do is, first of all, ignore this. We'll completely forget about this. Okay, so we will, so you just, this is always fixed, so you just forget about it. So the first path corresponds to S naught. There's nothing there, and that corresponds to the fact that this starting point is also on the line y equals 1 minus x. So there's nothing to do here. Okay, so there's no path over here. Okay, now for the next one, this path 3, I mean the second row, sorry, which starts with 3, has nothing there. So it does not go through this this horizontal edge, but it has to reach the line y equal to 1 minus x. So what it does is it goes vertically. Okay. The next one is 5, 1. The next row starts at 5. It has a single 1. So you want to catch the horizontal edge containing the 1. Okay, and if you take this horizontal, if you have to start from here, you have to take this. If you take this horizontal edge, then you touch the 3, which you don't want. So you have to take this guy, and then you have to catch a 1. So you take this. Okay, sorry, I'm not on that very well. Okay, that's that. So this is the next one. The fourth or whatever S3 starts, I mean, corresponds to the row starting at 7, and there's a singleton 5. So what do? Well, you take the 5, and now you don't want to take the 3. Anyway, if you took the 3, you would be in trouble, and that corresponds to the fact that you cannot have a 3 over here. So then there is nothing else, so then you only take vertical edges, because every horizontal edge will give you a reading. So that's that. And the last one has 7 and 3. So what do? Well, you take the 7 first. And then you have to take the 3. So you can't take the 5, you take the horizontal edge, and now you can take the 3, and then you take the vertical edge to avoid taking this one. Okay, which you could not have done anyway, because then they would intersect at this line, and that's as you can see from here, you cannot have a 1 over here because there's no 1. Okay, is that clear? Okay. Notice that if this were a 1, then you would have turned right over here, and then this would be okay. Okay, so it's a kind of tricky reformulation of these TSSCPP arrays. Okay, so this. So the proposition is this is due to William Doran in '93. Now it's not completely trivial to even construct these things. So there is a bijection between TSSCPP arrays of order n, and therefore TSSCPPs inside a 2n by 2n by 2n box, and non-intersecting lattice paths families, let's say, starting at Si for 0 less than equal to I less than equal to n minus 1, ending on the line y equal to 1 minus x, and taking upright steps. Okay. Any questions so far? Okay. So this well, there's a bijection, meaning they're equinumerous, and there's a natural bijection, as I explained. With this labeling of marking of these horizontals. Okay. So now the problem is, so okay, this is one step. So we have converted it to non-intersecting lattice paths, but this is a problem because we don't have fixed endpoints. If the endpoints were fixed, you would get a determinant. But now it's like summing over many determinants. So this is a problem reminiscent of CSPPs, that is cyclically symmetric plane partitions, but in a different way. There you had the starting points and ending points fixed, but you had many subsets, and that was taken care of by adding the identity matrix. But this is now a very different kind of problem. And what do we do? So due to well, many people contributed, but mainly I think it was Stembridge. So Stembridge realized that such NILPs can be counted using familes. So it's rather a deep idea, I would say. So so rather than a determinant, what naturally turns out to occur is a Pfaffian, and he used this to prove the TSPP conjecture. So there was a conjecture of, I think, due to Stanley, for the number of totally symmetric plane partitions without self-complementarity. So these are inside an n by n by n box. And Stembridge formulated them again as non-intersecting lattice paths where the endpoints are variable, and there he was able to write down a Pfaffian, and he was also able to evaluate it. So he settled the TSPP conjecture, although which is just enumeration, not Q enumeration, not weighted enumeration. Okay, so all right, so we will. So now, what I want to do, and this will take, I think, both this in the next class, is to try to formulate. Is to formulate this as a Pfaffian. So Stembridge did this in much more generality. So remember, we had the LGV lemma for general graphs. Stembridge formulated walks in general graphs in that level of generality, but we will not go there. I mean, it will suffice for us to look at these graphs. But from the way we formulate it, you will be able to see how this works in general graphs. Okay, so because we are working with Pfaffian, so you remember what a Pfaffian is. It's the square root of a determinant of an even antisymmetric matrix. So we'll always need even paths, even number of paths. So and depending, so you see, and this is where we will use this trivial path over here. So if n is odd, so depending on the parity of n, so if n is odd, we will exclude that, otherwise we will include. We will either include or exclude the trivial path starting and ending at S0. Okay, very good. So now so I'll start this formulation, but I don't think I'll be able to finish. Okay, but let's begin. So let Tn be the set of all paths with starting points Si. Starting points Si where I runs from 1 to n minus 1 if n is odd, or from 0 to n minus 1 if n is even, so that we have always an even number, and ending on the line y equals 1 minus x. Okay. In particular, notice that we are including paths not only which intersect but which end at the same point. We are allowing all such things. Okay. Okay. So we want to enumerate number of NILPs in T. So number of non-intersecting lattice paths. Okay. Now, okay, so some notation. So let n bar be n if n is even, or n minus 1 if n odd. Okay, this is just to save myself writing n or n minus 1 depending. Okay, so now I remind you of the Pfaffians. So recall notation from earlier. M sub n bar is the set of matchings of 1 to n bar. So remember what these were, you know, you arrange 1, 2, etc. N bar is even, so we arrange them and we match them. I mean, we have chords connecting them. Okay. You know, and so if pi belongs to Mn bar, so if pi is such a matching, then we had defined chi of pi to be the number of crossings in pi, and sine of pi to be minus 1 to the chi of pi. Right? You remember this. Then we had said if A is an even anti-symmetric n bar by n bar anti-symmetric matrix, then we had Pfaffian of A is the sum over pi in Mn bar, and you write, so sine of pi, so pi equals I1 J1 up to I n bar by 2 J n bar by 2, sorry for the horrible notation, where Ik is less than Jk for all k. So sine of pi, you have A I1 J1 etc. A I n bar by 2 J n bar. Right, we have this formula. Okay, so okay, so now we are going to sort of complicate life a little bit by considering a matching. So we will pair lattice paths in Tn, paths in Tn with matchings for the initial points, starting points. Okay, so here is some notation. So, okay, I'll state some things today, and then we'll take off next week from there. So suppose pi is in Mn bar, and L, which I'll write as L1 to Ln bar, is some collection of paths in T. Okay, so yeah, so these are paths So slight mismatch of terminology. So the ith part, so Li starts at Si minus 1. Okay. So, and this because of slight mismatch of terminology. Oh no, you cannot say that. Sorry. So let us just understand that we will start from the bottom. So if n is odd, we will start from S0, otherwise we'll start from S0. So Li starts with Si if I is even, and with Si minus 1. Okay, should I? Maybe I said Si minus 1 and odd Si and even. Okay. All right. So okay. So now we are going to pair these. So pi is considered. You want to think of pi as a matching of the starting points. So we think of pi as a matching of the starting points of the SIs. So then define inv of L pi. L is this collection pi to be equal to the number of pairs ij in pi such that the ending points of Li and Lj are switched. That is to say, i.e. Li and Lj cross an odd number of times. You can say I less than j if you like. So basically, you have I, let's say, below j, and then Li ends up to the left of Lj. Okay. If I starts to the right of j, Li starts to the, ends up to the left of j. So there's a crossing. Okay, it's the number of such pairs, but we are not looking at all pairs. We are looking at only pairs which belong to pi, where I and j are matched. Okay. Then the weight of the pair L pi is W of L pi. This is equal to 0 if the endpoint of Li is equal to the endpoint of Lj for some I not equal to j. So if any two paths have the same endpoint, the weight is 0, no matter what pi is. Okay. Otherwise, it's -1 to the inv of L. Otherwise. Okay. Then the weight of L is W of L is the sum over all pi in Mn bar, sine of pi, this is the -1 to the number of crossings, times weight of L. So for each pi, we are going to take its sign, take its weight. Sign and weight are both plus or minus ones, right? So this will just give you a sign. This product will be plus or minus 1 for each pi, and we are going to sum all of them. Okay, so this looks quite complicated, so let me show you this. So let's take an example with n equal to 4. Maybe it's the simplest non-trivial example. So go back to so let me take the highest point over here. So this is 4 minus 2. This is S4. This is 2 minus 1, which is S3. This is 0, 0, which is S2. And this is 2 minus 1, which is S1. Oh, what did I do? So n is 4. Sorry, okay. I think I should take 0. This is because of the slide shifting. Okay, so let me use the same coloring scheme as before. So let me mark my endpoints. So here. Actually, don't need to go that far. So I'll take this particular path. So my L is fixed. It's this. Oh, maybe I should draw the line first. Okay. Okay. Okay, so there's an intersection. Non-trivial things are only going to happen from intersection. Okay, so this is that. So okay, so this is my L. And now for each pi, I'm going to so there are 3 possible pi's, 3 possible matchings of in M4. So let's say pi, in the first case is 1, 2, 3, 4. So let me match it. Okay. So for each pair ij, we will see if there is any matching. So remember, what is inv of L pi? We want to look at number of pairs ij such that ending points of Li and Lj are switched. That is Li and Lj cross. So so there are only 2 pairs. So let's look if okay, let me write it 0, 1 and 2, 3 just to be keep our sanity check. So here is 0, 1, 2, 3. So 0, 1 they do not cross. 2 and 3 they do cross. So inv is the number of such pairs. So inv of L pi is 1. And so weight of L pi is minus 1. It's minus 1 to the 1, which is minus 1. Okay. Now the next is 0, 2, 1, 3. So okay. Now let's see. Among 0, 2 is the do the paths 0 and 2 cross? Well, no. Do the paths 1, 3 cross? No again. So in with 0, and so weight is +1. And lastly, pi is 0, 3, 1, 1, 2. So let's check. Do 0 and 3 cross? Well, no. 1, 2 cross? No. So again in with 0. And weight is +1. So therefore, what is weight of L? Weight of L is this sum. So we have to sum over sine of each pi and the weight. So sine of okay, so let me not. So what is sine of pi? Number -1 to the number of crossings in pi. So there's no crossing in 0, 1, 2, 3. So it's +1 times -1. So sine times weight plus, here there is one crossing, so that's -1 to the 1, which is -1 times +1, this weight. And the last one has no crossing, also 0, 3, 1, 2. So that's +1 times weight is +1. So this is -1 plus -1 plus 1, which is -1. Okay. So what good does this do? This is proved by the following lemma. So here's the lemma. Number of non-intersecting lattice paths in Tn is the sum over all lattice paths in Tn W of L, which is therefore the sum over all pairings L pi sine of pi weight of L. Okay. So if you sum over all these weights over all paths, no matter where they end, you will get precisely the number of non-intersecting weights. Okay. That's what we will prove next time. I think I don't want to start this proof because it's a bit involved. But this essentially will help us write down this as a Pfaffy. Okay. So any questions? Okay. Let me stop recording.